Okay, welcome back. In the last class, we have looked at different transformation products from austenite to pearlite above the nose and austenite to bainite below the nose. And if you are doing extremely fast cooling or rapid cooling, we have seen that austenite would transform to martensite. So, we have stopped the discussion at this particular slide where we are discussing the transformation, martensite transformation. As we have already mentioned, the transformation of austenite to martensite is a diffusionless transformation, and hence there is no change in chemical composition, and the small volumes of austenite suddenly changes its crystal structure when you are rapidly cooling the austenite, rapidly cooling the eutectoid alloy. The small volumes of austenite suddenly changes its crystal structure, and the transformation proceeds only during cooling and ceases if cooling is interrupted. That means, if you stop continuing to reduce the temperature beyond martensite start temperature, martensite further reaction from austenite to martensite, further transformation of austenite to martensite will not happen. Hence, the transformation depends only on the decrease in temperature and is independent of time. So, at a given temperature, even if you keep for sufficiently long time, however long you keep, the transformation will not happen, because the martensite transformation is only a temperature dependent transformation. It always happens at a constant temperature, and it happens readily, there is no time involved there. All right. So, the amount of martensite transformed with reduction in temperature is not a linear function. That means, if you are reducing the temperature from martensite start temperature below, the amount of transformation from austenite to martensite does not scale linearly with the temperature reduction, and the number of martensite needles produced at first is small, and then the number increases, and finally near the end it decreases. So, it is like an S-shaped curve, where initially you have a small accumulation or small transformation, small amount of transformation of austenite to martensite, and in between, after that the transformation rate will be more. So, that means at higher somewhere in between temperature, here when I say in between, it is not the time but the temperature, right. At a very close to martensite start temperature, you will have the martensite needles produced at a very low, and as you are in the middle range of this martensite start to martensite finish temperature, then you will have reasonably steep increase in number of martensite needles, and finally it decreases again. So, the temperature of the start of martensite transformation is known as MS, or martensite start temperature, and the temperature at which martensite transformation finishes, that means when austenite transforms to martensite completely, then it is called martensite finish temperature. If the steel is held at any temperature below MS, then the transformation to martensite will stop if you are holding at that particular temperature, and will not proceed unless the temperature is dropped. And so, the martensite transformation of a given alloy usually cannot be suppressed. If you are doing it a very fast, if you are cooling the alloy at a very high rate of cooling, if you are hitting the martensite start temperature, it will transform from austenite to martensite, right. So, there is no way that we can suppress this, and nor the MS temperature, the martensite start temperature also cannot be changed by the cooling rate. It only depends on the alloy composition. So, for a given alloy composition, martensite start temperature is fixed and the martensite finish temperature is fixed. You cannot change those temperatures for a given alloy. All right. So, as we have seen, as you are reducing the temperature, as you are initially, the martensite transformation will be less, and as you are further reducing the temperature, the martensite transformation picks up, and again in the end it slows down. Okay. So, the temperature range of the formation of martensite, so that is martensite start temperature to martensite finish temperature. So, this is sort of your martensite start temperature, and this is probably martensite finish temperature. So, this range during which the martensite transformation happens from austenite is a characteristic of a given alloy and cannot be lowered by increasing the cooling rate. So, it does not depend on the cooling rate, and as we have already mentioned, MS temperature is a function of chemical composition only. So, if you are talking about 1080 steel and 1090 steel, their martensite start temperature and finish temperatures are fixed. This one will have a specific martensite start temperature, this one will have a specific martensite start temperature. So, the martensite start temperature depends only on the chemical composition, not on the cooling rate. So, theoretically, the austenite to martensite transformation is never complete. That means, you will not have 100% martensite transforming to 100% austenite transforming to martensite. So, theoretically it is never complete, and small amounts of retained austenite will remain even at low temperatures. Okay? Some amount of, so whenever we are saying that martensite finish, it is not necessarily 100%, probably 99%. So, remaining 1% austenite is retained, has retained austenite. So, the transformation of last traces of austenite becomes very difficult as the amount of austenite decreases. Hence, the MF temperature, the martensite finish temperature, is clearly not defined, as there is always some retained austenite in the product. So, the martensite is the hardest and most brittle microstructure that is obtainable in a given steel. So, for a given alloy composition, of iron and carbon, for a given steel alloy, the martensite microstructure is the hardest and brittle microstructure that one can obtain. And the martensite hardness of steel is a function of carbon content in the steel. We know that as you increase the carbon content, you will increase the hardness and brittleness. Similarly, the martensite hardness, amount of hardness, is also a function of carbon content. So, the martensite results by cooling from austenite temperature rapidly by quenching before perlite can form. So, how do you get it? So, you actually, before the perlite can form, you quench it. So, that quenching means rapid cooling. You rapidly cool austenite such that no perlite is formed, and all the way you bring the temperature down to martensite start temperature, and that is when your austenite transforms to martensite. So, the quenched martensite structures are too brittle because of the rapid cooling rate and the microstructure development. They are known to be extremely brittle, and hence they cannot be used for applications right away unless they are tempered. So, they should be undergoing, all the martensitic microstructures should be undergoing another heat treatment process called tempering. Only the tempered martensite will offer some additional strength and toughness. Otherwise, in its quenched form, martensite is extremely brittle to be used for any technological applications. So, reheating the as quenched martensite to a temperature just below A1, that means lower critical temperature, results in the best combination of strength and toughness. So, you need to do another heat treatment process after obtaining quenched martensite. So, the as a function of carbon content, the martensite hardness is shown in this figure. As you increase the carbon content, your martensite hardness increases. Of course, beyond certain value of carbon content, the martensite hardness levels off. So, martensite is never usually in a condition of real equilibrium, because it is a non-equilibrium phase, although it persists indefinitely at room temperature. It may persist at room temperature, but it is not in a equilibrium phase. So, in that sense, the structure, the martensite structure, can be considered as a transition between unstable austenite phase and stable mixture of ferrite and cementite, right. It is some phase in between unstable austenite and a stable perlite microstructure. And as we have discussed, it is potentially very hard material. Although martensite is harder than austenite, extreme hardness is possible only with sufficient carbon content. If you do not have enough carbon content, you may not have good enough hardness. So, and another reason why the martensite shows extreme hardness is because of the severe lattice distortion that is caused by the trapped carbon atoms in the lattice. So, typically, so people, when they were studying about martensite transformation of austenite to martensite under rapid cooling, people were thinking that this martensite kind of transformation, that means the diffusionless transformation, was believed to be unique for steel for several years. People thought this is a special phenomena in steels. However, there are after several years of studying different other alloys, the martensite transformation was observed in many other alloy systems such as iron nickel, copper zinc, copper aluminum, nickel titanium, and so on. So, a special class of materials called shape memory alloys involve the martensite phase transformation, wherein there is a diffusionless transformation, and hence they sort of give very interesting properties where they can remember their shapes. That means, you take a shape memory alloy at room temperature, and then you apply certain deformation, and then you can, if you supply some additional heat energy then the material goes back to its original configuration. Even if you impart plastic deformation, it sort of remembers its original shape and it goes back to its original shape, right. So, here I am showing you one video which actually describes the shape memory effect of a nitinol alloy, a spring made of nitinol alloy, and this you can actually view at this particular YouTube link. So, this here we can see that the spring, which is a shape memory alloy made of nitinol, is being deformed plastically. So, you have a permanent deformation there, and then you actually give very complex deformation and rather large deformation. The strains are also large, you can see here, it is not small strain and very complex deformation. And then now certain additional heat energy is produced, heat energy is provided such that it undergoes some phase transformation such so as to get back to its original configuration. You can see that with the supply of this heat energy, there is some transformation happening, and then the entire spring is regaining its original shape. It is not elastic deformation that is getting regained, even if it is plastically deformed to another state with very complex deformation, you are able to regain the shape, right. So, this kind of systems are nowadays these class of materials are called smart materials, and they have several applications, particularly in medical industry and aerospace industry and so on. Okay. I encourage you to go through certain literature that is available on shape memory effect in several textbooks or the online resources. Alright. So, now we have seen the time temperature transformation diagram or isothermal transformation diagram for a eutectoid steel. However, how does such a time temperature transformation diagram looks like for a non-eutectoid steel, either hyper-eutectoid steel or a hypo-eutectoid steel. Here we are showing the TTT diagram for 1.13% weight % carbon steel, which is a hyper-eutectoid steel. So, when we are cooling down this guy, the microstructure that we would expect from our study on phase diagrams is that you will have a pro-eutectoid cementite. So, austenite first transforms to pro-eutectoid cementite above the lower critical temperature A1, and once it touches A1, then it starts transforming to eutectoid mixture of ferrite and cementite. So, you have a pro-eutectoid cementite phase and a perlite phase. So, you can clearly see here you have an additional curve which basically represents your pro-eutectoid cementite phase. So, if you are at eutectoid temperature and above that you will have transformation to pro-eutectoid cementite phase. So, that is why this region is A plus C, that is cementite, and once you are below the eutectoid temperature, then you will have transformation from the remaining austenite, whatever austenite is remaining. So, some amount of austenite is transformed to cementite and remaining austenite would transform to eutectoid mixture of perlite, so ferrite and cementite, that is perlite. So, that is what is basically, if you are cooling down to 700 degrees Celsius and then you are waiting here, and then you see that between point A1 and A2 you will have a austenite A1 to A2 austenite transforming to cementite, right, and between A2 and A3, A2 to A3 austenite transforms to perlite, and at the after A3 you will have the microstructure has pro-eutectoid cementite plus perlite, right. So, you can see this additional curve represents this pro-eutectoid transformation as we have already discussed, and here what you will know is how much time does it take for austenite to transform for a given alloy, for this is 1.13 per weight % carbon. So, you can see that if you rapidly cool it down, the amount of pro-eutectoid phase reduces, you can see that, right. So, here at higher temperature the amount of pro-eutectoid phase is more, and at lower temperature the pro-eutectoid phase, the pro-eutectoid fraction of pro-eutectoid phase is going to be less, and most of it will be converted to perlite. So, by looking at this, you can actually design your cooling cycle in such a way that you can get the amount of cementite, pro-eutectoid cementite that you want in the microstructure, right. Alright. So, this is a phase the time temperature transformation diagram for an alloy steel 4340 steel, right. So, here 4 represents the type of alloy, what type of an alloy steel is this, and 3 is the 3% of that particular predominant alloying composition, and 0.440 represents 0.4% carbon, right. So, for this particular guy you see that the time temperature transformation diagram looks much more complicated, right. So, here you have austenite, here because it is 0.4% carbon you will have pro-ectectoid ferrite phase. So, that is why you have austenite plus ferrite, and then you will have austenite plus ferrite plus perlite, and then ferrite plus perlite, right. Ferrite plus perlite is because pro-ectectoid ferrite and remaining is perlite, and here you will see that bainite, austenite is transforming to bainite below the nose, and this is a little bit more complicated TTT diagram, but nevertheless you will have again there is martensite start temperature, 50% martensite transformation, 90%. Here nowhere we have seen MF, because as we have discussed martensite finished temperature line is very difficult to identify, because always there is going to be some amount of austenite that is going to be retained. So, there will not be 100% martensite line, it is very difficult to identify such line. So, usually most of the TTT diagrams will show martensite 90%. Alright. So, now let us look at effect of different cooling rates and the resultant microstructures of the eutectoid alloys. We are paying attention to eutectoid alloy, so that is 0.8% carbon. So, here we have 8 different cooling curves, and we will see what sort of a microstructure one would get for each of these cooling curves, right. And okay. So, here this is cooling curve 1, and from cooling curve 1 to 8 we have increase in cooling rate, and my apologies for this. So, this here this is x1 x subscript 1. So, it got messed up when because of the version change from PowerPoint, but anyway. So, this is x1, x2, x3, x4, x5 and so on, and this is your x6 and this is your say x7, right. Alright. Okay. So, let us look at what is going to happen in these systems. So, for instance, let us look at cooling curve 1, right, that is this guy, and we have shown in between on that line we have shown a green hatched line. That green hatched line represents the transformation progress scenario, right. So, here you can see that as you are reducing the temperature. So, here x1 is very slow cooling rate, and you can see that the transformation begins until transformation does not begin until the time x1 corresponding to x1 reaches. So, until this time the transformation does not start, and there the transformation begins. So, transformation begins at x1 and ends at x1 dash, and we can see that here we have the transformation is happening at very high temperatures, and at high temperatures the nucleation rate is low, but the diffusion rate is high. Since the nucleation rate is low, the number of nuclei formed are few, and as a result the microstructure will be a coarse microstructure. So, the end product here is going to be coarse perlite, and besides each and every microstructure we have also written the hardness, Rockwell hardness on Rockwell scale C. Here you can see that here Rockwell hardness 15, and as you are coming down the hardness increases, because you are increasing the cooling rate, the hardness also increases. So, here you have a coarse perlite. Okay. And note that here when you are cooling down, you can see that at this temperature you are not waiting at constant temperature, you are continuing to reduce, for instance here. So, the austenite that has been transformed to perlite here is happening at higher temperature compared to the transformation of austenite to perlite here at this location. That means, here is at lower temperature compared to here, which means the perlite microstructure is also going to have a gradation. It is coarse perlite overall, but again within that you will have the grains of austenite transforming to perlite here will have a larger size compared to the grains of austenite transforming to perlite here, right. So, there will be a slight change in the size of perlite that is forming in the beginning and in the end, and after x1 prime you do not need to wait to continue to cool at the same rate, because all the transformation has happened. Now, you can rapidly cool it down. So, this sort of an information is going to be extremely useful for industry, because you know until what time you need to wait for a complete transformation of arsenate to perlite, and after the transformation has happened you can actually cool down at a much faster rate, because you do not have any non-equilibrium phases staying there anymore, right. Further cooling down will only reduce the temperature of the component. Alright, now let us look at cooling curve 2. This is x2 and this is x2 prime. So, the transformation begins at x2 and ends at x2 dash, and this is sort of represents isothermal transformation. That means you are actually at constant temperature, you are holding the specimen at that temperature, and then you can see that because it is at constant temperature, the perlite grain size that you are getting will be uniform throughout. However, the size of the grain will be smaller than the what has been produced in this region, because the temperature here is lower. So, you will have a uniform grain size and the size of the grain will be little smaller than this coarse perlite. So, it is somewhere between these two sizes, right, and this size and that size. Alright. So, you will have a uniform coarse perlite and the transformation finishes at x2 prime, further after which we can actually cool down rapidly. And now, let us look at x3, this is x3, this is much faster cooling rate, and you can see that there is actually the range about which you are cooling is actually larger compared to first x1 prime, x1 prime range. So, this is typical. So, a faster cooling rate of this range is typical of a heat treatment process called normalizing. We will see what is normalizing. So, normalizing uses a higher rate of cooling, whereas the first one where x1 dash, that is sort of representing your annealing process. Okay. So, the transformation begins at x3 and ends at x3 prime, and you can see that the microstructure of the perlite is medium perlite, because it is going to be finer than coarse perlite, that is why it is called medium perlite. Again, in this case also you will have a size variation from the perlite that is formed in the beginning to the end. So, you will have a greater variation in fineness compared to x1 prime, because there is a larger temperature gradient. And now, let us look at curve 4. This is x4, is much higher cooling rate, and you can see that this is very close to slow quenching. It is not quenching, but it is not very slow cooling rate. So, it is also a cooling rate much faster than normalizing. So, again microstructure will be starting from medium perlite. So, in this region you have medium perlite, in this region you have fine perlite. So, the microstructure will have a medium perlite to fine perlite variation. Alright. And now, the x5 is interesting, the cooling curve 5 is very interesting. It is a typical of an intermediate cooling rate. You can clearly see here, this is your transformation start line, transformation start, and this is transformation end line or finish line, and this is transformation 25%. So, that means when you are cooling down along this region, for instance x4, by the time it reaches here you will have only 25% of your arsenate transformed to perlite. Now, if you come here on the x5 line, it is becoming tangent to this curve. So, suppose if you are seeing here, what will be the transformation? That will be less than 25%. That means, the moment this cooling curve becomes tangent to one of the transformation fractional lines, that is when the transformation stops, right, because below that the transformation is actually less than 25%. That means, there cannot be any transformation happening, and that is the reason why you do not have this green extending throughout this region, only this region the green is there. So, that means, transformation happens only from here to here. That means what? By the time it reaches here, for x5 to x5 dash, you have 25% perlite and remaining 75% is austenite. You still have 75% austenite, and you are continuing to cool down at the same rate, and then you do not have further transformation, and then you are hitting Martenset start temperature at x5 double dash. The moment you are hitting Martenset start temperature at x5 double dash, that is when the austenite, remaining austenite, 75% remaining austenite will start transforming to Martenset, and the Martenset transformation, say, so let us say this is finishing or 90% Martenset is transformed, or we will in this case we let us assume that it is finished temperature, then the remaining 75% austenite would have transformed to Martenset. So, here the microstructure will be 25% perlite plus 75% martensite. That will be the microstructure. And now let us look at x6 and 7. If you see x6 curve, for instance, let us look at x7 first. It is actually tangent to your martensite, the transformation start line. That means it is never going into the two phase region. That means there is no transformation of austenite to perlite that can take place. So, this rate of cooling is what we call a critical cooling rate, the cooling rate below which only the austenite to perlite or bainite transformation takes place, above which the austenite will not transform to either perlite or bainite, it will directly transform to martensite. So, you can see austenite, the 7 cooling curve 7 ends here actually. If it is ending here, what happens? At this temperature you have stopped, that means you are not further reducing the temperature. So, all the microstructure will be only of austenite, because you have not transformed further, you have not reduced the temperature further, because the martensite transformation requires you to go below the, you continue to reduce the temperature. If you do not reduce the temperature, even if you wait there for sufficiently long time, no transformation takes place. Now, look at the 6. So, 6 continues to cool down. So, here it is continuing to cool down, that is when all austenite is transforming to martensite. So, here microstructure will be 100% martensite. Okay. And let us look at cooling curve 8. So, how does this look like? So, you can see that you can see here it is very high cooling rate, but you are not continuing to cooling down, you are holding at this temperature, and this temperature is your below the nose. The moment you are coming below the nose, all the austenite will have to transform to bainite, right. So, that is why you see that this is all transforming to bainite. So, the microstructure here will be 100% bainite. This is basically a medium, here very close to nose will be upper bainite, far away from the nose will be lower bainite. So, it is somewhere close to lower bainite. All right. So, now let us look at, by learning how these cooling curves work, let us try to solve this problem. For an eutectoid steel specimen, initially at 700 degrees 60 Celsius, 760 degrees Celsius for sufficiently long time, so that it has complete austenite. So, it is completely austenitized. Now, if it is in complete, all the microstructure is austenite, now identify the microstructure that would be obtained in the end for the following 3 cooling campaigns. So, first one is, if you take this guy and rapidly cool to 350 degrees Celsius, hold for 10 power 4 seconds. Let us look one after the other. Rapidly cool to 350 degrees Celsius and hold for 10 power 4 seconds, and then quench to room temperature. So, here you have these cooling lines drawn. Rapidly cool to 350 degrees Celsius. So, that is this guy, and then wait for there for 10 power 4 seconds. So, you are waiting there for 10 power 4 seconds. So, you are actually missing the nose. Since you have missed the nose, the transformation, it is above the martensite start temperature. So, here still bainite can form. So, during this process, by the time it comes here, the bainite would have, austenite would have transformed to 100% bainite. So, you will have completely here the microstructure will be 100% bainite. So, for the case A, you will have 100% bainite. And for case B, rapidly cool to 250 degrees Celsius, hold for 100 seconds and then quench to room temperature, right. Rapidly cool to 250 degrees Celsius, that is 250 degrees Celsius, and then hold for 100 seconds. 100 seconds is this, and then I am holding for, I came below the nose and I am holding here for 100 seconds. Even after holding for 100 seconds, we did not hit the transformation start line, this red line, and hence no transformation of austenite to ferrite takes place, austenite to bainite takes place, but then we are quenching it down, and hence what should happen here? All the austenite will be transforming to martensite. So, that will be 100% martensite. And the case C, rapidly cool to 650 degrees Celsius, hold for 20 seconds and then rapidly cool to 400 degrees Celsius and hold for 1000 seconds and then quench to room temperature, right. So, first rapidly cool to 650 degrees Celsius and there hold for 20 seconds. So, this is 10, so 20 is somewhere here. So, we are holding for 20 seconds, that means it is, if it is not written, that means it is 50% line. If nothing is written here, right, whether it is 25% or 50%, if it is not written, then it means it is 50% line. So, what happens here? Austenite transforms to, by the time here in the C, austenite is transforming to 50% perlite. Is it fine perlite or coarse perlite? Here you have coarse perlite, so it is 50% coarse perlite. Microstructure is coarse. And then you are suddenly cooling it down, because now you are not allowing it to go continue and you are cooling it down. Only 50% of it is converted to perlite, and you are continuing cooling down at 400 to 400 degrees Celsius, and then your time starts again, right. That is why this dashed line, just to show that your time starts again, and again you are waiting for 1000 seconds. This is 1000 seconds and you are waited here. So, what happens? Because you are now by the time you are quenching, you are actually going below the nose here, and hence as a result you will be the remaining austenite, if at all hits, it is hitting the transformation start line. So, the remaining 50% austenite. So, you have 50% austenite and 50% perlite, by the time 50% austenite, 50% perlite. So, the remaining 50% austenite will convert to the 50% bainite total. So, here all the austenite, all the remaining austenite will convert, right. All the remaining austenite is converting, means it is 100% is converted. What is actually available out of the original composition? Only 50% is available. So, that whole 50% is converted to bainite. So, you can see that the third one has 50% perlite and 50% bainite, right. All right. So, that is about the isothermal transformation, but now let us actually look at what happens when you are continuously cooling, because the continuous cooling is something that would happen in the industry, not usually the isothermal transformation. So, that is why the continuous cooling is very important. So, the transformation on continuous cooling is something that we would look at. So, the IT diagram in isothermal transformation diagram cannot be used when the cooling is done continuously, and hence you need to modify the diagram for transformations that occur as the temperature is constantly changing. So, what happens is, so this here the dashed lines represents your isothermal transformation diagrams, and then the because if you are doing continuous cooling, then your the transformation start time and the transformation end times are going to increase, as well as the temperatures are going to reduce. So, for a continuous cooling, the time required for reaction to begin and end are delayed, and the diagram is called CCT diagram, that is continuous cooling transformation diagram, as opposed to TTT diagram. However, here because we are doing continuous cooling, these two curves change, but the Martenset start and Martenset finish temperatures will not change, because they do not depend on the cooling rate. So, because of this fact, for our eutectoid steels, you can see that because if you are doing continuous cooling, you will see that you will not have the nose region below the nose region. So, your transformation finishes above the nose region itself, right. So, here you have two cooling rates. The blue curve represents a slower cooling rate compared to the red one. The blue curve is typical of full annealing heat treatment process, that we will discuss at a later stage in this course, and the red curve represents moderately rapid cooling, which is typical of normalizing. So, these are the two cooling rates, and since the in the case of continuous cooling, the bainite is usually not transformed when you are dealing with eutectoid steels, as the transformation to perlite would have finished before it reaches the bainite temperature, right, because you are continuously cooling. So, you would always finish your transformation by the time you hit the nose, right. So, by the time you hit the nose, all the austenite has already transformed to perlite, and hence there is no possibility for transformation of bainite in the case of continuous cooling in eutectoid steels. So, that is why diagram does not have lower nose region, and the line AB, the transformation terminates along the line AB. All right. So, we know that the cooling rate is called critical cooling rate when there is no transformation of austenite to perlite, but all that means it basically misses the nose, then you can see that this 140 degrees Celsius is cooling rate represents your critical cooling rate. All right. And however, for an alloy steel, which is a more complex steel than a eutectoid steel, you can see the nose region. So, the bayonet formation is possible for alloy steels, but not for eutectoid steel as we have seen before. The carbon and other alloying elements, what they do is they shift the perlite and bayonet noses to longer times and thus decreasing the critical cooling rate. So, bayonet formation is possible for non-eutectoid plain carbon steels, it is possible. Only for eutectoid steels you see that it is not at all possible. So, this is the CCT diagram, continuous cooling transformation diagram shown for 4340 steel, whereas before we have seen the time temperature transformation diagram for the same steel. Okay. So, for different cooling rates one would be able to find out what is the microstructure. Here we have shown different cooling rates, the critical sort of boundary cooling rates. For instance, if your cooling rate is between this blue line and the orange line, you will always form this such a microstructure, martensite plus ferrite plus perlite plus bayonet, right, because you will have this austenite to pro-eutectoid ferrite in this region, right, and then so somewhere in between. So, suppose here this guy will give you pro-eutectoid. So, by the time 100% transformation would happen, so you will have pro-eutectoid ferrite plus perlite. Here you will see only the pro-eutectoid phase is formed, after that it is not getting in. So, the remaining material which would have transformed to eutectoid mixture of ferrite and perlite is not transforming, and hence it goes in, and hence you will see that you will have some bayonet transformation also is taking place in this region, right, and then remaining, if at all it is not hitting the bayonet finish temperature, you will still have some martensite forming. So, that is why in these each of these regions you can see what is a possible microstructure that can be generated. All right. So, with that we will close the discussion on the time temperature transformation diagrams and continuous cooling curves or continuous cooling transformation diagrams, and in the next class we will look at heat treatment of steels, and particularly we will pay attention to two important heat treatment processes called annealing and normalizing. Thank you.